In this video, we are going to be looking at estimates and estimators. Really, ultimately, what we're going to go towards is what we call interval estimation, but we're going to have to kind of run up to that. So first, let's just talk about estimates. Right? We've been estimating things for much of this course, especially once we got into Chapter 4, when we started calculating sample means, sample variances, so on and so forth. Those were all estimates of the population parameters, right? Now, what we want to do here is to talk about some of the characteristics of those estimators and pin down what we're talking about, kind of define a few things. First, we're actually going to start by defining what an estimator is. All right, an estimator is a strategy or rule used to estimate a population parameter. So something like the sample mean, or X bar, would be an example of an estimator, right? The actual equation for the sample mean, right? X bar equals the sum of xi divided by n. That is a rule, it's a strategy, right? Once we put data into that, right, we can get an estimate of that population parameter, right? But the actual equation itself is an estimator. So an estimator is the rule or strategy. The estimate is the result of that. So this is the actual number. So for example, X bar equals the sum of xi over n. That is an estimator. That's the rule or the strategy. Now, if we go out and we gather some data and we go and calculate that the sample mean for something is, say, 12.8, 12.8 is not important, it's just a placeholder, right? But once we take a sample, right, and take that data, apply it to the estimator, right, actually do that calculation using the data, right, the number we get, the result we get, is the estimate. Right, specifying it a little bit more, we also have different types of estimators. X bar, and a lot of the estimators that we have looked at, X bar, sigma, or not sigma, S, so the sample standard deviation, or S squared, the sample variance, those are examples of what we call point estimators. So with our point estimators, probably can kind of figure this out. All right, they use a single point, all right, a single value to estimate the population parameter. So just like when we're calculating a sample mean, we're only going to get one value as a result. We're not going to get multiple values for our sample mean calculation. The same is true for our sample variance, for our sample standard deviation. We just get one value for that estimate. That's why it is a point estimator. Now, point estimators are very useful. We use them all the time. We've been using them throughout this course. So, well, I guess I haven't really brought this up. However, there is a criticism of point estimators, right? And while they are very useful and they're very good, right, they don't really give us a lot of information about the accuracy or precision of our estimate, right? We just get a single value and we aren't going to know, really how accurate that is. All right, so a solution to this is to use what we call an interval estimator. An interval estimator is going to give us an indication of potential error, right? Which is just the flip side of accuracy. Right, so how much we can, how far off we can expect to be. All right, more specifically, a interval estimator is going to define an upper and lower boundary that hopefully contains the population parameter. All right, so we say hopefully here because other than a few exceptions, probably just one exception really that we're going to talk about here in a second, we're never going to know if our population parameter falls into our interval. Right? So we want to construct an interval that's going to make it as likely as possible that we're going to get that population parameter in there. Again, we're never going to know for sure, except for in probably one extreme case, again, that we're going to talk about. But, right, so we hope that it falls in there. So speaking of hoping that our population parameter falls into our interval, it's really easy to create an interval that contains any population parameter. So any population parameter we're looking for, we can create a interval that will contain it. Doesn't matter what it is, you don't even have to tell me what the parameter is you're looking for. I can create an interval that contains that parameter. Right, that interval is negative infinity to infinity. Right? That contains all of the numbers that there are, so our population parameter has to fall in that interval. However, this isn't very helpful, is it? So just because the interval is wide and it contains the population parameter, that's not in and of itself going to be useful. We also want to have as narrow an interval as possible. So I think of it somewhat like this. Right? Let's say that your dishwasher is broken, and you call a repair person to come over and fix it. And they say, I'll be there between 8 a.m. and 8 p.m. Right? They've given you an interval that they're going to arrive in, but are you going to be happy with that interval? Probably not. It's a really wide interval that's not very useful. That person is essentially telling you, stay at home all day and I'll get there when I get there, right? You're not going to like that. If instead that repair person said, I'll be there between 11 a.m. and 12 p.m., right? So 11 a.m. to noon, then that's a much better interval, right? It's narrower, it gives you a better idea of when they're actually going to be there, instead of a very wide interval. So we want our intervals to be as narrow as possible. That's going to give us the that allows us to have the most accurate idea of kind of our accuracy, how much error, how much potential error we're going to get. The more accurate we can be with that, the better our estimator is. What we're about to do next is we are going to derive essentially a interval estimator. We're going to try to create one that is going to work for us, that's going to work well for us. Now, the properties, the features that we're going to take advantage of to create this interval estimator, we've already covered in the last chapter. Right? We're going to return to a lot of the properties bestowed by the central limit theorem. So just as a reminder, the central limit theorem states that if our sample size is greater than or equal to 30, then the distribution of the sample mean has these properties, right? It's approximately normal, the distribution is approximately normal, the expected value of x bar equals mu, right? So that's our unbiasedness kind of property, and then our standard error, the standard error for the sample mean, can be calculated using sigma divided by the square root of n. All right, so why is this important? Because our distribution, the distribution of our sample mean, is approximately normal, then we can use the standard normal distribution to help us create this interval.